So let's go ahead and take a look on the next page at some various examples of this chain rule, just so we can get a little bit more familiar and comfortable with it. So the first thing I do when I take a look at this equation is I try to identify if there are any inside and outside pieces. That way I know which piece goes where when I apply my chain rule derivative shortcut. So at first glance, notice how the power of 3 is on the outside of those parentheses. So I can label this as my outside, and then everything inside the parentheses I can label as my inside. So when it comes time to do the chain rule, we need the derivative of the outside. So this power of 3 would come down. We need to keep the inside stuff because we haven't really dealt with that yet. We're only doing the derivative of the outside portion. So we'll bring down the 3, we'll keep the inside, which means we have to drop the power by 1. And then we need to multiply by the derivative of the inside. So when you look at what you labeled as the inside, the derivative of 3x squared would be 6x, and we got to add the derivative of 2, which would just be 0. All right, so we'll leave it like that. Now, like I've said so far this year, I can't really tell you how far to simplify these things because I don't know what's going to show up as a multiple choice selection. So if we just tried to clean this up a little bit, we could do 3 times 6x to make that 18x, and then we can leave this other quantity the same. Now you could take the time to write it twice, go through a FOIL process, combine like terms, distribute in the 18x. So it might take you some time, but notice how this is pretty simplified the way it is. Let's go ahead and try the next one. So it kind of has the same setup. Notice how we can clearly label 2x plus 5 as the inside part, but we should really think about rewriting this root just like we have in previous examples, and we can make it a power of a half. Okay, so instead of the square root, we're going to use that power of a half as the outside portion. So for the derivative, we got to take the derivative of the outside, so that involves bringing down the 1/2, keeping the inside. The new power would be negative 1/2, and then to finish off our chain rule, we have to multiply by the derivative of the inside, which would just be 2. So if we clean this up a little bit, 1/2 times 2 would cancel each other out. So we're just left with this quantity to the negative 1/2 power. And if it's a negative power, we can turn it into a fraction, bring it to the bottom to make the power positive. But you also could change this quantity back to a root since it's a power of a half. So either one of these would be okay to write as your final derivative. Again, I don't know what the multiple choice response would look like, but we have to be familiar with either one of them. Let's go ahead and try the next one. So it's another root example. We can change this into x plus 2 to the 2/3 power because we have the power of 2 on the inside and the root is a 3. So going through our chain rule, the derivative of the outside, so if we take the time to label, this would be out and this is in. So we'll bring the 2/3 down, keep the inside, new power would be negative 1/3, times the derivative of the inside, which would just be 1. So that's not really changing anything. If we rewrite it, we can move the negative power to the bottom. That way it becomes positive. Right, so there's one possible result for your derivative, but you could change it back to a root, and it would be a cubed root of x plus 2. So again, either one of these would be perfectly acceptable. All right, if we check out the next one, let's go ahead and rewrite it. So we have the coefficient of 5 out front, and instead of a cubed root, I'm going to write it as a power of a 1/3, and we'll have x squared plus 2x on the inside. So this is just rewriting the original function. Let's go ahead and apply our derivative. So we can label outside, inside. So we're going to bring the power down, which would make it a 5/3, keep the inside, new power would be negative 2/3, and then we've got to multiply, finish the chain rule process by multiplying by the derivative of the inside, which would be 2x plus 2. So we're going to clean it up, make it a little bit more eye appealing. The negative quantity, or the negative power, can move to the bottom of the fraction. So we can write that next to the 3, which means the 5 and the 2x plus 2 are still up top. So if we wanted to rewrite this, we could distribute in the 5 to get 10x plus 10. And then if we wanted to, we could rewrite the bottom back as a root. So this would be the cubed root of x squared plus 2x squared. All right, let's check out some trig examples. So trig are tricky, okay, not only because it's trig, but also the way we denote certain things within the trig function. For instance, this power of 2 really means we have the cosine of 3x, okay, that whole thing being squared. So if we take a look at inside versus outside, the power of 2 we can label as out, and then the cosine of 3x can be our in. So our derivative, we would need the derivative of the outside, so we'll bring down the 2, keep the inside, new power would be 1. Then we have to multiply by the derivative of the inside. Now if you take a real hard look at what you labeled as the inside, we have cosine of 3x. And if you take a look at that portion even more closely, we have another inside and outside piece. So if we just consider this portion, notice how cosine is now the outer function and 3x is the inner. So this is when it can get pretty good because we're already in the chain rule process, but in order to finish it by taking the derivative of the inside, we're going to have to do another chain rule. So here's the derivative of the initial outside, keeping the inside, and then we've got to multiply by the derivative of the inside, which involves another chain rule process. So we're going to repeat it. The derivative of our new outside would be negative sine, okay, the derivative of cosine. We got to keep the inside, which is now 3x, and to finish off our chain rule, we got to multiply by the derivative of the inside, which is simply 3. So it's kind of a process. We had a chain rule within a chain rule because we were able to identify multiple inside and outside pieces. So everything's being multiplied together. If we were to combine everything, we'd have 2 times a negative 1 times a 3, so that would give us negative 6. And then we'll have a cosine of 3x to the first times a sine of 3x. So there's our final derivative. If we take a look at the last one, it's going to be pretty similar. If we move the power of 2 where it technically should be, we have sine of 2x plus 1, that whole thing being squared. So when we initially take the derivative using our chain rule, we're going to need the derivative of the outside. Maybe we'll label them appropriately. So we'll bring down the power of 2. We'll keep the inside part, new power would be 1, times the derivative of the inside. Now when you look at the inside portion, okay, sine of 2x plus 1, we technically have another outside inside pieces. So we can label sine as the outer function and 2x plus 1 as the inner. So really, to find the derivative of this inside, we have to go another chain rule process. So the derivative of the outside, the derivative of sine would be cosine. We'll keep the inside times the derivative of the inside, which is simply 2. So all this is being multiplied together. We can combine things appropriately. So 2 times 2 would be 4. We'll have a sine of 2x plus 1 times a cosine of 2x plus 1. So there's our final derivative. All right, so chain rule can be a little bit overwhelming. I know at least the last two, when you had to do it twice, you're probably thinking, oh my gosh, what did we just do? But as we go through this section and have our practice day or homework day, we're definitely going to be able to identify which shortcuts should be used and when they should be used. So we definitely will have some practice when it comes time to this chain rule derivative shortcut.